So we're talking about these two different types of bonds, okay? And so actually, I don't know which slide to put it on, this one or that one. I gave you the electronegativity values. So at the top of this, if you wanted to, you might write the Greek letter these. That's the electronegativity values. That's what I just gave you. Okay, don't say I never gave you anything. So we use the electronegativity values to come up with electronegativity differences. And I mentioned water. So water has this sort of thing where you have a central oxygen atom, and it is chemically bonded to two hydrogens. So when I say electronegativity differences, all we got to do, by the way, electronegativity differences are delta chi. And I think the other day I said basically what you're going to do, I need to throw away that. All those are getting dead. We're going to take the absolute value of the electronegativity of atom A minus electronegativity of atom B. And I don't think in my notes anywhere I say that. And I'm not sure it says that in any textbook, but by golly, that's what you do. So we're going to use this little table here, and I'm going to look at the electronegativity of the oxygen atom, the electronegativity value, Pauling value, it's the same thing. You're looking at 3.5. There are no units. The electronegativity of each hydrogen is, looking at 2.1. So I could assign the delta chi, or electronegativity difference for both of those, because they're the same thing. Delta chi is equal to the absolute value of, I usually take the big one minus the little one so I don't have to change it up. 3.5 minus 2.1, and that's equal to 1.4. Okay, so that's what we mean when we're talking about electronegativity differences. And so here in a minute, you're actually going to see that the tipping point is like 1.8 or 1.7. What happens then? Actually, an electron will be transferred. Not transferred here, it's shared. Okay, so remember that the way this works, actually, this is an important aspect of a water molecule. Water molecules have this kind of boomerang shape, which is kind of fun. We'll be talking more about that in this unit of material with the lone pair electrons around the oxygen. But the fact that the oxygen is more electronegative, actually that carries a partial negativeness because it's higher electronegativity, and electronegativity is attraction of electrons for itself. So we're going to call this actually partially negative. And to show the word partial, I know it drives us nuts, we have another Greek letter. It's going to be like this, partially negative. Partially negative. Why? Because it's higher electronegativity. What's this guy down here? Well, relative to 3.5, 2.1, it's lower. So it's actually going to be giving up some of its electrons. We'll call that partially positive. This Greek letter actually is a lowercase delta. This is an uppercase delta. This is a lowercase delta. They look nothing alike. Okay, but so anyway, that's what we're talking about. So the deal is, in a case like the oxygen, the hydrogen, and water, electrons are shared. Okay, I told you, we kind of talked about it, that if you have a metal, then probably an electron was transferred. I said, all intents and purposes of identifying a metal in a compound, hydrogen is a nonmetal. So hydrogen's a nonmetal, and I kind of made a big deal of it. Oxygen's a nonmetal on our periodic table. So if you have all nonmetals, then your actually electronegativity differences are going to be less than the 1.7, 1.8. Electrons are going to be shared. Otherwise, electron will be transferred. So broadly speaking, we can kind of have these different types of bonds. If your delta chi electronegativity difference, delta chi, same thing, if it's 0, what does that mean? It means you took one minus the other one, and they were the same, right? Got 0. A really good place that happens is in our diatomic elements. Like we have our copper nickel, our hydrogen, copper nickel, okay? These are all diatomic, these all make molecules of two atoms bonded together. In each of these cases, you know, we can pick on hydrogen. Hydrogen looks like this. Electronegativity of each of them is, what did I say? Pauling says 2.1. So of course, delta chi here, again, we're characterizing that chemical bond is absolute value of 2.1 minus 2.1. Okay, that's a pure covalent chemical bond. Opposite of that, we have an ionic bond. And I mentioned the 1.8, 1.7 threshold. It kind of depends on which chemist you talk to, what their day is like. But if this delta chi gets too high, then by golly, what's going to happen is an electron is going to jump ship. Should go this way. Electron's going to jump ship from the low electronegativity to the high one. An example of an ionic compound, we can just kind of do that math here, is Na.Cl, so sodium chloride. Let's check it out. Our electronegativity of Na, I'm like in 0.9. So metals have low electronegativities. That means that if they're bonded to something, you're like, hey, take my electron. I've got low electronegativity anyway. The electronegativity of the chlorine atom, you're looking at 3.0. So to characterize that chemical bond, the electronegativity difference is 3.0 minus 0.9. So you get a whopping 2.1. 2.1 is greater than 1.8. So that's why we've seen a little video, I think. An electron is literally transferred. We'll be talking more about that again today and tomorrow. But an electron is transferred. It's kind of a stepwise thing. That leaves the sodium deficit electrons. So it's deficit specifically 1, so it makes a +1. The chlorine picks up an electron. That means it's rich by 1 electron. It makes it a -1 charge. And it's the electrostatic charge between these two ions that creates that. We call that an ionic bond. So just so we're all on the same page, ionic bond is electrons transferred, and here, electron shared. Electrons. So if it's not enough to go ahead and for it to jump ship, if it doesn't meet that delta chi is 1.7, 1.8 or greater, what can happen, and this actually happened in the case of our water molecule, you end up with, what did we say, delta chi there was 1.4? Wait, yeah, sorry. We said that the electronegativity difference here is 1.4. So that's what gives us a covalent bond. Covalent, electron shared. It's covalent, but it's not shared equally. Who gets more of it? Well, the one with the lower electronegativity. And this will come in handy for a week from tomorrow's lab. Remember we said that the trend in electronegativity for group A elements looks like this. Electronegativity increases as you go across the group and increases as you go from bottom up. And you can actually see that for this. All right. Cool. So I have some slides to kind of look at that. So for the chloride chloride molecule, Cl to Cl, you're looking at a perfectly covalent bond. Delta chi is 0. Here, actually, electrons are not shared equally. If you look at chlorine, you're talking about 3.0, hydrogen 2.1. So can you see how the chlorine is kind of swollen? I think that's probably what they're trying to say. Actually, that would be partially negative, and the hydrogen is partially positive. The example that we looked at an ionic compound, remember, if you have a metal in it, probably the metal is going to go ahead and give up an electron or 2 or 3. Okay, so again, if the formula has metal, probably got at least one bond there where an electron has been transferred. If you have, and that's ionic bond, if you have one ionic bond in all of your compound, that makes the whole formula or compound ionic. No metals, you're talking about electrons are shared, maybe not equally, but shared between all the atoms that are stuck together with chemical bonds, and you have a covalent compound. You don't need this. This is just kind of a small one here. So I also brought you this. I can't use this on text. So the homework that you guys just handed in. Wait a minute. No, I'm so confused. Should I say it again? You guys have to do. Yeah, you guys do electron configurations. Okay, good. So can you kind of see the sheet I gave you? Can you tell that the font for chromium, atomic number 24, the font for chromium is a little different. Remember we said that chromium is the first place that we have electrons around a chromium atom do not follow Low's n plus L rule. And honestly, I don't know if you can tell, but kind of it's colored though from what I printed it from. But the weird font ones or the lighter font, those are actually our exceptions to the n plus L rule. But we said, I kind of brought this because I thought it'd be easier to kind of talk about valence shell electrons. So the valence shell electrons are the highest n. So if I just, I've got my contacts in this morning today. So if I just pick on, let's look at TEs. That's tellurium. I get my TEs mixed up. 52. Yeah, okay, tellurium. Okay, so it's krypton. Beyond krypton, you have those, let's see, 18 electrons. You can see how they're configured. You see that the highest n is 5. Okay, so wait a minute. Yeah, I'll cross out here. Can you see we have 2 electrons in the 5s and 4 electrons in 5p. 2 plus 4 is 6. There are 6 valence electrons for tellurium. I'm going to go ahead and remind you, I think something I pointed out before. For the main group elements, that's these 2 columns and these 6 columns, I could have told you 6. And here's how I could have told you 6. I could have just gone up and looked at the group number. Okay, 6 valence electrons. See how that works? Valence electrons are important because we're going to see that those are the electrons that either are going to get kicked off for that atom to become a cation, like the metals kick off with all of their valence electrons, or we're going to see that an atom will go ahead and bring up an electrons to go ahead and cap that off at 8, and they'll become a negatively charged anion. All right, so why do atoms lose electrons, gain electrons, or heaven forbid share electrons in the covalent bond? It's all about trying to get the configuration like this, a rare gas configuration. Okay, now I can use the word octet. For these guys, you're talking octet, but can you see for helium, you're talking duet. Duet. These guys are octets. We're going to see that hydrogen doesn't want to get an octet because dang, it only has 1 electron. It's like, dude, I can get 1 more electron and I'll still keep my hydrogen core. I'll get 1 more electron and then I have electrons that match with the rare gas helium. So that's a duet. Okay. So again, as we continue to kind of beat on this idea about atoms being joined together in a compound, which is such an exciting thing. It totally is. It's very underlooked by people. We're going to see that electrons are lost, gained, or shared to get the rare gas configuration. All right. So there's a certain place I want to get to in part 5. I think we're going to be in good shape. I never know. I don't know if I talk 100,000 miles an hour or what the deal is. But I feel like I never know how long things are going to take. But my point was going to be, when we get to the blank slide, then we're good to go for tomorrow. And tomorrow's lab, if you don't mind, if you would, I think this is right. No, I think we should get far enough. We might have to do some slides tomorrow, but the slides, I think, are already in your lab manual. All right. So we're focusing on electrons being transferred, ions, and forming ionic compounds. So the JAG up there, here we have the group A elements, kind of get your bearings. We have group 1A, 2A, and then we have 3A, 4A, 5A, 6A, 7A, and 8A. I know you see the 1, 2, 13 through 18, which I don't like as well. And on the sheet, the black and white sheet, and the periodic table you get on your exams, and the periodic table that's on the bound notes that you purchased. If you look at the top, they have the designation like I prefer. Anyway, we see the JAG, and we see the JAG, things on this side of the JAG, on the left of the JAG, are our metals. And we're going to see that they're going to lose electrons to become like, when I say the rare gas in the period before them. See how this is all shifted? Like here we have lithium and beryllium are period 2, but actually helium is period 1. Okay, sodium and magnesium are period 3, and neon is period 2. Okay, and I should have circled aluminum. So they're going to kick off those valence electrons. So metals kick off valence electrons. And actually, let me go back one more. These guys are going to become cations. Cations. They're going to be positively charged. Makes sense. They lose the negative particle, then they get positively charged. Well, let's look at the other side of the jag. And it's like for us visual people. Over the nitrogen, you would have seen 5A, 6A, 7A, and of course these are 8A. And these are kind of even more fun to look at because we're going to see that they pick up electrons. We're going to say 3, 2, or 1 electron, and they're going to become like the rare gas in the period at the end of the period. Now, when these atoms go either kicking off electrons like metals do or taking in electrons like nonmetals do, just keep in mind that the core stays the same. The nucleus with the protons, remember the protons are what makes an atom what it is. The protons and the neutrons stay embedded. It's electrons that kind of come and go. So down here, I'm going to put the word anions, and I'm not going to put a minus sign. Anions, negative. Not to be confused with cations and anions. Cool. Well, we're going to be talking in a week from tomorrow. We're going to talk about make Lewis structures, but we have this thing kind of like a Lewis structure called an electron dot formula for the elements. And all it is here, this is what I'll do. I'm going to show you that carbon is a 4A element, nitrogen is a 5A, 6A, 7A, and 8A. So with that in mind, I told you that the group number, the A anyway, tells you how many valence electrons. So right here, hopefully you can make a connection, that those dots represent the special valence electrons. So carbon, silicon, germanium, tin, and lead, they all have 4 valence electrons. So we can show carbon abbreviated, like this slide says, that carbon, that letter C would represent the nucleus of the carbon atom and the non-valence electrons. All right, so it's all about octets. So here, can you see at a glance that neon has 8 dots around it? It's group 8A. It's all about octets. So neon is set. Like the slide said, the whole north, south, east, west, there's no specific really thing about it being north, south, or east, or west. All right, helium. So let's kind of take a look at what it looks like when a metal like sodium becomes a cation. So sodium is 1A. It has 1 valence electron shown there in its Lewis dot formula. We can kind of use a chemical equation to represent the loss of 1 electron. And then over here, I'll put a +1. Plus or +1 means the same thing. It's the same thing. So this says it loses 1 valence electron from its N is equal to 3. So are we good with that? So find sodium. It's atomic number 11. So you see where that includes from. So basically it loses that 1 electron 3s and it becomes a rare gas like neon. Okay. So now if we were to go ahead and show we call that a cation, positively charged cation, +1 cation. Now if we were to show the structure of the +1 cation, we would show its new set of valence electrons is actually 8 because it's like neon. Okay, that's it. So that was a metal. Let's look at a non-metal. So non-metals form negatively charged anions. So if we pick on fluorine, fluorine is 7A, okay? And actually, if we find fluorine on here, it's atomic number 9. We can see beyond helium, it's got the 7 valence electrons arranged, 2s2, 2p5, right? 7 valence electrons shown here. It almost feels to me like if you have a kid playing with cars, goes, you could take one car and you could park it right there. Okay, so it takes in 1 electron, and here we go. It parks it right here. Now it has an extra electron, and that's why it made the negative charge. So negative without a number is the same thing as -1. And you can kind of see where, fluorine atomic number 9, you can see where it picks up an electron, where's it going to go? Well, it's going to go ahead and fill up the 2p subshell. Instead of 2p5, it's going to be 2p6. Well, let's pick on sulfur. So relative to fluorine, sulfur is down 1 period, and it's back over 1 group. So sulfur is 6A, so we must have 6 valence electrons around it. That works. On its way to 8, to get 8, it's going to pick up 2 electrons. So here we go. If it picks up 2 electrons, we're going to show that the whole species is charged, we're going to use brackets. And then outside the brackets, we'll put its charge. So if we find sulfur on here, atomic number 16, you can see it's neon. Beyond neon, we have 2 electrons in the 3s and 4 electrons in the 3p. Okay, so that's the 6 electrons, valence electrons we see there. We pick up 2 electrons, and then we completely fill the 3p. That works. And now it has a rare gas like, well, the one at the end. Now it has a rare gas like argon. All right. So in tomorrow's lab, we're going to be dealing with we're going to be dealing with ions. Of course, an ion is a cation that's positively charged, an anion is negatively charged. We're going to be dealing with ions that have more than one atom stuck on them. Those are called polyatomic ions. What we've been talking about in the lecture are monatomic ions. Okay? And we said that the metals will lose electron or 2 or 3 to become positively charged cations. We said the nonmetals will pick up an electron 2 or 3 to get an octet, and they'll be called anions. Negatively charged anions. All right, so then we have some trends. The beauty of having a periodic table, and this one isn't a good example, but the periodic tables that you have for tests, it's power. It's just power, right? Pure power. Because if you look at 1A, 2A, and 3A, you know that they're gonna form a +1 because they're gonna kick off that 1 valence electron, a +2, okay? Then over here, the metal beginning with aluminum, that's gonna be your +3 cations. And it's gonna pick up those 3 valence electrons. So it kind of looks like this then. Group 1, this is the group 1. You can see that they're going to form a +1 charge, lose that valence electron. 2A, lose their 2 valence electrons, form a +2 cation. And then you got to be careful with the 3A, because boron is I don't think it's a metalloid. Boron is a non-metal, so it's not going to form a cation. But aluminum down, these are metals, and they will lose electrons. They'll lose specifically 3 electrons. Okay? Yes, ma'am. Okay.
So what about the ones in the middle?
The ones in the middle, like, yeah, they could go either way. You can't hang your hat on them. And in tomorrow's lab, I say hang your hat on. And you can hang your hat on these. You can feel the power. These are +1. These are +2. And these are, and I don't have any more volume listed up there, but I think you could go, these are +3. I don't know, did you mean by these guys?
Yeah.
Yeah. These guys have, like I said, these guys can form multiple oxidation states, multiple different cationic forms. So in tomorrow's lab, they're actually going to be our second tier. I'm going to have to tell you which one we're dealing with for the metals. Okay, so this actually just kind of, we've been talking about how our electronics is configured, and so this would match up with the sheet I gave you, except the sheet I gave you has these 10 electrons, 1s2, 2s2, 2p6, those 10 electrons, it has a bracket neon, okay? So if we were to show you the one valence electrons, the highest end that kicks off, it's going to be this guy right here, isn't it? So on a test sometimes, and in homework, you will have to go ahead and write the metal cation. Show the electron being kicked off. Which electron is kicked off? The highest end. And here in a minute, I kind of expand on that. If you have two options, the same end, same highest end, it's going to go from the lowest L first. Which remember, L is equal to 0, that's S. L is equal to 1, that's P. L is equal to 2, that's D. L is equal to 3, that's F. So if we pick on aluminum, aluminum is 3A, so we should expect to see the 3 valence electrons we do over here, 2 in the 3s and 1 in the 3p. And so when we write the +3 cation of aluminum, where basically those guys go away. And the next slide, maybe it's the next slide, could it be already? No, maybe. Talks about a thing called isoelectronic. And it sounds like an awesome word, but all it means is, iso in this case means same. So here, can you see where we have the same electron configuration here for the Na+1 as we do for the Al+3? Now, the hearts are different, okay, because you have the heart of a sodium atom and the heart of an aluminum atom. But with regard to their electrons, they are the same. Happens all the time when ions form, isoelectronic. So this is where I said, if you go ahead and look at how the electrons are configured, identify the valence electrons, given a choice, they're going to leave first from, they're going to leave first in the highest value of L. So yeah, so if there's an SP, I'll go first from the P and then from the S. All right, so Logan asked about these guys in the middle, so we'll go ahead and take a look at this guy. We'll take a look at an important iron. And actually, this is a pretty good period. All periodic tables are different. Notice this periodic table for Fe has a +2 and +3. Those are the two different oxidation states, two different versions of cation forms. Okay, so let's take a look at what that would look like with regard to what we know about how those 26 electrons around a neutral iron atom, what they look like. So using the lowest n plus L rule, the arrow diagram, we would come up with the electrons are configured this way. Okay, and actually this is kind of fun because we last talked about how you can use the position of the element in the periodic table to do your handiwork. So this is D block, right? So we have S, P, D, and F. So actually the last electrons added were D, specifically, like Twister, 4 minus 1 is 3, specifically they were 3D. How many? 1, 2, 3, 4, 5, 6. So see how that is 3D6 up there. But, and you don't have to do this, you can see maybe already in your notes, in order to emphasize the highest end, what we can do is kind of unscramble them in order of increasing n. If we do that, we see that the real important guys here are in the 4s subshell. 2 electrons in the 4s subshell. Okay, so we have 2 valence electrons. So, and you might be asked to do this on a test. If you on a test are asked to write how the electrons are configured around an ion, I always write the neutral atom first, and then I either, in this case, take away electrons or add electrons to my neutral. And it's easier for me. So if we're talking about the +2 cation, it must lose 2 electrons. Well, which 2 electrons are going to, you can see it lost, okay, or these guys. Okay, but over there, it's got +2 and +3. So here we go. If it loses 1 more electron, notice that its new valence shell, these guys right here, right? And we said it's going to kick off from the highest L. So S, L is equal to 0, P, L is equal to 1, D, L is equal to 2. So this one more is going to go. So there you go. And actually, the other day, we talked how if there's 5 boxes or 5 orbitals in any D-type subshell. So if you half fill it, smiles all around. It's extra stable. So this is a reasonable sort of thing for the plus 3 cation, the Fe that has lost 3 electrons. All right, so let's switch gears to the nonmetals. And specifically, I'm only going to commit myself to the nonmetals beginning with 5A, 6A, and then 7A. Of course, 8A, they don't want to do anything. They won't lose electrons, they won't gain electrons, okay? So, and this is where carbon can actually kind of go either way a little bit. Carbon and silicon kind of follow each other. So beginning with the 5A, okay, we're going to actually see that, I don't know how you want to look at it, but 5A, these guys, I kind of use my fingers. They go 1, 2, 3. So I have to pick up 3 electrons, and in doing so, they're going to be in -3 charge. The 6A, excuse me, these guys pick up 2 electrons, -2. And these guys here, the halogens, 7A, pick up 1 electron, become -1. So I mentioned the power, and especially with my intro Gen Chem students, I emphasize that, feel free to, on this test or any test, take your periodic table and mark it with what you know. What do you know? Well, you know that these are going to be a +1, a +2, a +3, begin with aluminum, and then I usually go backwards from the other way. I go begin with oxygen, I'll be -1, nitrogen a -2, fluorine a -1, oxygen a -2, and nitrogen a -3. See, I don't have my group 8A up here. So, all right, so let's look at electron configurations of those nonmetals picking up electrons. So chlorine would look like this. Let's just kind of see how that works. Notice that if we want to write the abbreviated rare gas notation, we're going to base it on the rare gas in the period before it. And then beyond that, we go across and we pick up electrons. So this is the S block. So beyond neon, I'm going to have 2 electrons in the 3s. So that's why you see 3s2. And I jump over here, and then I go 1, 2, 3, 5. Where are they going to be? Well, it's P block. So it's going to be P, specifically 3P. So that's why it's 3P5. So now it picks up 1 electron. And where's it going to go? Well, it's going to find a home, completely fill, like a full house for that 3P subshell, 3P6. Take a look at phosphorus. Phosphorus is 5A. You can see the 5 valence electrons here. And so yeah, phosphorus and chlorine are the same period, so it's just a couple electrons less, isn't it? So notice to get a complete octet, it needs 3 more electrons, and it does so to become a -3 charge. So the core neon, beyond neon, is 3s2, 3p6, which is actually the rare gas in the period that it's also in. So you're looking at argon. So I mentioned isoelectronic a little bit ago. So you definitely have isoelectronic species here. Chlorine is isoelectronic, sorry, the chloride ion, the Cl-1, is isoelectronic with a P3-, isoelectronic. Sounds like a good vocab word to throw out there. Okay. Isoelectronic. So if we kind of pick on neon, what happens here? Well, the nonmetals are going to pick up electrons to be like neon, which is in period 2. And the metals in period 3 are going to kick off electrons to be like neon. So as it turns out, these are all isoelectronic with neon. I guess I should emphasize electronic. I mean, like again, their core, same number of protons, same number of neutrons. So they're not the same, but electron-wise, they are the same. Because everybody wants to be like a rare gas. So you have these non-metals picking up electrons, becoming negatively charged. These metals kicking off electrons, all of their valence electrons become positively charged. All right, so now this is getting into what we're going to do tomorrow. So the word bi in binary means two. So tomorrow we are going to be looking closely at ionic compounds that are just made of two ions. Now we're going to kind of kick it up a notch. There's kind of 3 notches in tomorrow's exercise. The 3rd notch in tomorrow's exercise, we will be dealing with ions that are polyatomic, not monoatomic. Polyatomic ion, you've heard before, like phosphate, nitrate, sulfate, perchlorate, nitrite, perchlorite. They just, things are hypochlorite. Yeah, there's a perchlorate. Perchlorate. But anyway, those things that have more than one atom joined together to make an ion. So, but in this case, we're going to actually just focus on when you have a cation from a metal that's lost electrons and you have an anion from a nonmetal that's picked up electrons. And I'm going to show you the crisscross method to make it what this says, this 3rd bullet says, electrically neutral. 2 things you have to be able to do on your test. That is to make a neutral, you have to be able to make a formula that's neutral. Like the formula for table salt, NaCl. Is it neutral? Yes. I'll show you how it is. Okay. But in neutral, it has no net charge, even though you have cations and anions involved. So, not sodium chloride, but sodium fluoride. And maybe you're already kind of seeing a pattern. Notice that a long time ago, we said that elements in the same group, in the same column, behave similarly. So it's not so surprising that sodium chloride that we know and love is similar to sodium fluoride. So we said that the sodium, since it's a sodium at the top of the column, you would show a +1. It's going to lose that valence electron and become positively charged 1. Fluorine, you would show -1 at the top of the column. It's going to pick up 1 electron, form a -1 charge. And there you go. Okay, so I think of it kind of stepwise. This is the electron transfer we've been talking about to make the cation and the anion, to make the cation and the anion. And then I like to show my chemical bonds that are ionic bonds as a dot, 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 dot. Here's my dot, 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 my ionic bond between those, the cation and the anion. But when we talk about neutral, can you see where this whole thing, it's got a charge going on. Oops. It's got a charge going on, but it's got a 1 +1. Goodness gracious. And it's got 1 -1. You're like, Mrs. Snipes, did you really need to write that down? Yeah. So that math reflects this. Oops. Okay. So sodium, these are both going to lose that valence electron, become a +1 charge. And sulfur, notice I only count 6 dots, 6 valence electrons. And sulfur is a 6A element, so that's all consistent. To become an octet, like argon, it needs 2 electrons, and you can see those sodiums each want to give up an electron. So that's a wonderful sort of thing. You see the electron being transferred, okay? And in doing so, each one of those sodiums now is a +1, and this sulfur thing is a -2. So let's do the math down here. With regard to sodium, well, I think I'll go up here. With regard to sodium, we have 2 sodiums, and they are both a +1, because that's what sodium does. And we have 1 sulfur, and it's a -2. That's what I mean by neutral. That's just a quick check. Is that my blank sheet? Okay. So, to kind of get you set up for tomorrow and the crisscrossing and things to think about, and there will be more things to think about, but this will get you down the road to the first of 3 parts. I call it my closets. I call it my metal closet, which gives me my cations, and my non-metal closet, which gives me my anions. And you could just like close your eyes and point to one. But let's pick on strontium. Let's say somebody says, I am going to make an ionic compound. I'm going to have metal in it. So I bet it's going to give up electrons, become positively charged. And then I'm going to go to my other closet. And let's pick on sodium. Wait, sorry, nitrogen. I said sodium when I was looking at nitrogen. Let's pick on nitrogen, okay? So nitrogen's my non-metal, strontium is my metal. So on a test and in your exercise, you might need to combine those two. So my first item of business would be to go ahead and rewrite them and say what charge they are. So I feel awfully powerful at the top of my 2A, having a +2. So next to my strontium, I'll put a +2. My nitrogen, that column, 5A, for nitrogen phosphorus. Arsenic's metalloid, so I just go nitrogen phosphorus for that one. My 5A, it's going to pick up 3 electrons and become a -3 charge. So the crisscross I talk about, and kind of in context of what we just covered in lecture, it looks like this. I need to write a formula, and I'm not going to write the electron dot formula. I just want to write a regular old formula to make this a neutral, okay, knowing that they have these charges. So crisscross looks like this. So the number of strontiums I need is the magnitude of the charge on the nitrogen. I almost said it again, on the nitrogen. So in other words, I need 3 strontiums. The number of nitrogens I need is actually the magnitude of the charge on the strontium. I need 2 nitrogens. That's my crisscross. So if we do a check down here, notice I've got 3 strontiums. Each one of them is a +2. And then I've got 2 nitrogens. Each one of them is a -3. So when I do that math, it's neutral. So that's the crisscross, showing you kind of the neutral thing. Now, some of the pitfalls, and I'll be looking for this tomorrow, is for whatever reason, we see people trying to kind of make these subscripts hover, making them superscripts instead, and no, that's not right. And the other thing I see is people want to write the charge. No, we don't write the charge. If you have a periodic table and it's a 1A, 2A, 3A, or if it's a 7A, 6A, or 7A, 6A, or 5A, you know that you can hang your hat on the charge. Okay, so that's one of the things we'll be talking about tomorrow. And then tomorrow, I think I'll go ahead and leave the whole naming part. You guys will do fine with it. But it's not really that complicated, but you guys just need to get it, and so you can do it on your test. That's a good place. That's where I want to get. So see you, I'm pretty sure in here. I will double check that I booked this room. I think I did.